Okay, continuing on with section 10.5, let's look at one final example. The costs of 30-second ad slots during the Super Bowl have increased greatly, even when adjusted for inflation. Let C be the cost in millions of dollars of a 30-second ad slot at T years since 1960. And then they've listed some different Super Bowl numbers with the Super Bowl year and the cost in millions of dollars for the ads. So they want us to find the linear regression function and call that L, and the exponential regression function and call that E for this data set. Before I find either of those, I'd like to plot the data with a scattergram and see whether it looks like the linear regression is a better idea or the exponential regression is a better idea. So the first step in doing that would be to take these years and convert them to values of t. And t is the number of years since 1960, so we'll be subtracting 1960 from all of these. In 1971, that had been 11 years, 16 years, 21, and so on. When you switch to a new century, that can be a little confusing, but just do your subtraction over again. 2000 minus 1960 would be 40, so 2006 minus 1960 would be 46, and then this one would be 49. So now that I've figured out the values of t, I'm going to want to take those and put them into L1, and then these costs I'm going to want to put into L2, and that way I can make a scatter plot on the graphing calculator and have a look at the pattern. So I'll go ahead and turn that on. I want to go to the Stat menu and choose Edit, enter in those values of t. And then move over to L2 and enter the cost of the ads. And then I want to do a scatter plot. But before I do a scatter plot, I want to make sure my window is correct. So I'm going to go to the window settings. Right now it's set for -10 to 10, but my input values go from 11 to 49. So it might be more appropriate to go from like 0 to 60. It's a little below this and above that, giving 10 years about, roughly, on each side. And then I could number in maybe 5-year increments. For the outputs, the Y values, 0 would be a minimum, and the max is 3.0, so maybe go up to like 3.5. Sorry, I'll get that minimum back at 0 and the max at 3.5. And then for the scale, maybe every $500,000 we could make a tick mark. So now I think the scale will display the data. Now I just want to make sure the data is set up, so I hit the Y equals menu, and I notice that my plot 1 is not highlighted, so that nothing's going to graph right now. So I'll use the up arrow, press enter. That'll highlight that, so that plot will graph now, and I always have that one set up to be a scatter for L1 and L2. So if I hit graph, I should see the data displayed. And both a linear and a exponential seem like they would be a decent fit. I could imagine drawing a line through there that gets pretty close to those points. On the other hand, I do see a little bit of a bending pattern to that. And if I really think it's bending or curving, then probably the exponential will be the better fit. So at the moment, that's kind of my hunch, is that exponential will work better than linear. In any case, they want me to do both. So I'll start off with the linear regression function. So stat, calc, linear regression, number 4, and my data is in L1, comma, L2. So it looks like for the linear regression, we get a slope of 0.069349 and so on, and the intercept is -0.8378. Alright, so let me write those down. So for the linear function, I'll write L of t is equal to mt plus b, or at plus b, so 0.0693495 times t minus the intercept 0.837828. I didn't see anything here about rounding rules for how many decimals they wanted, so I just put a lot. Better to have too many than too few. When you're on My Math Lab, make sure you just follow the rules for what they want you to put there. So that's linear regression like we did back in chapter 5. Now let's try an exponential regression and see what we get for that one. So same idea. I'm going to hit the Stat button. I'm going to go to Calc, but this time I'm going to go down further and I'm going to find the exponential regression, which is down here at number 0. So highlight that, press Enter, do second L1, comma second L2, and it's going to give me a y equals a times b to the x, and it's telling me the a and the b. So I want to write those down. So the exponential function, e of t, would be 0.140625 times the base 1.064929 raised to the t. And I wrote a 9 there because that was an 8 followed by a 6. So that's using linear regression and exponential regression to come up with the equations, and that's what they asked us to do, right? Find the linear regression equation, find the exponential regression equation. And then they're going to start asking us to make some predictions. But to me, it makes sense that if I want to make predictions, first I'd look at those with the data and see which one fits better. So let me go ahead and show you how that works. So I'm going to bring the calculator back in, and I'm going to enter these two functions into the y1 and y2 area so that I can see their graphs with the data. So y equals, for y1 I'll enter this one, 0.0693495 times t, or the x button on the calculator, minus 0.837828. So there's one function, the linear one, and now the exponential, 0.140625 times 1.064929 raised to the t, or I'll use the x key. Just a quick comment, there's parentheses here that I didn't put in the calculator. When you only have a single number in parentheses, they're actually optional. Here they're just kind of visual to help us separate that number out from the t and cause a clear visual break. So as we hit graph, we'll see our data, and then here comes the line, decent fit, and here comes the exponential, and because it's curving, it can follow along that pattern of the data, and I would say that it seems like that one is coming closer to the data values overall. So when it comes time to make predictions, in general I would say I'd rather go with this exponential one for this data set than the linear one, because it's coming closer to more of the data I see, so it probably would do a better job of predicting the data that I can't see as well. Alright, so let's go ahead and start doing that job. So let's read part B and see what they want from us. Use L, your linear function, and E, your exponential function, to estimate the cost of a 30-second ad slot during Super Bowl I, which was in 1967. The actual cost, adjusted for inflation, was $200,000. So which function did the best job of modeling the situation in 1967? Well, if you take 1967 and you subtract away the 1960, which was our starting point, then you get t equals 7. So we want to plug that into both of the two functions. So looking at this one, we want to put the 7 in here and therefore also there. So L of 7 would be equal to 0.0693495 times 7 minus 0.837828. And then I also want to do the same thing for the exponential function. I want to plug the 7 in here, and so then also as the exponent right there. So E of 7 would be 0.140625 times the base of 1.064929 raised to the t, which is going to be 7 for this particular problem. Alright, so we'll bring in the calculator now, and we'll see what we get for each of those two. So I'm going to hit second quick, get back to the calculation screen for the linear one, 0.0693495 times 7 minus 0.837828, and I get a negative, which is interesting. Just a little strange, right? So I'm just going to double check that I put that in right. 693495 times 7 minus 0.837. It looks like that's correct, though it can't possibly be correct for the situation. Does it say how to round it? No. So I'm just going to put a lot of digits there. Negative 0.3523815. I'll just put everything I see. And then let's see what we get for the exponential one. So for that one, we have our base of 0.14, sorry, our multiplier out front, 0.140625 times our base, 1.064929 raised to the 7th. And for that one, I get approximately 0.218427. So I think putting 6 decimals is actually ideal for this because these are in millions of dollars. So if we take L of 7 and we multiply that times a million, that would move the decimal over 1, 2, 3, 4, 5, 6 spots. And I'll go ahead and round to that nearest dollar, so I'll make that 1 round up to a 2. So I'm going to guess for the linear one, negative $352,382. And for the exponential one, that would become, move the decimal over 6 spots when you multiply by a million, so 1, 2, 3, 4, 5, 6. That's going to be $218,427. So the linear equation is predicting that an ad for the first Super Bowl didn't actually cost you money, that you were paid $352,382 to put an ad on. Of course, that makes sense. Nobody's going to pay you to put your ad on. We skip commercials. We don't pay to see them, right? So that seems like a bad prediction to me. And yet this $218,000 is very close to the $200,000. So what I think they want us to get out of this little experience is to see that because the exponential function fit the data better, and let's bring the graph back in, right? Because it fit the data better, you'd expect better predictions. And we can also kind of see what's going on. Why do we get a negative? Well, look, the line disappears below the x-axis, so it becomes negative right about there. And 1967, I think we might have used a scale of 5. So 1967 would have been like, I think, right around in here, which is a negative zone. But of course, it doesn't make sense. And if you look at the pattern of the data, it looks like it's curving this way, not going down. So getting this 218,000 seems like a better plan to go with that curved graph rather than the straight one. Not just because it's closer to the right answer, but because it follows the data pattern more overall. So their strategy with these questions seems to be pick a point, show that one function works better than the other, and therefore exponential is better. I actually would disagree with that. I think that the exponential is better because it fits the overall pattern of the data better. I'm not going to focus on just 1967 and see which one does a better job. I want to look at the whole data set and see which one does a better job. And when you do that, it definitely seems to me like the exponential fits better. So they do this just to kind of confirm that for us, but for me it's more of a visual thing. Look at the data, does it look more straight or curved, and then do your two equations and graph them, and then which one seems to get closer to the points. It seems to me like the exponential one is better, a better fit, and so when they ask me to make predictions, I'd want to make them with the exponential. I would trust that one more. Alright, so continuing on with that problem, let's look at part C. Find the slope of graph L and the base of E and describe what they mean in the situation. So we have these two different kinds of models, one for a linear pattern, one for an exponential pattern, but then the numbers we get from those also get interpreted in different ways. So let me bring in that previous page so we can look at those two functions. So for the linear one, the slope would be the coefficient of t. Let me just put an L here. So the slope would be the change in output, which was really cost. So I'm going to put change in cost over change in input, which would be our t. And then that was 0.06939495 over 1. Then what are the units on that? Since it's cost, it would be dollars, right? Except for that it says in the table that it's actually millions of dollars. So I'll multiply by $1 million. And then the t was time measured in years, so I'll put a year. When I multiply by the million, the decimal is going to move over 6 places. So that goes over 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right there after the 9. So that would be $69,349 and I guess 50 cents if we want to keep that 0.5 over 1 year. So what is that telling us? For each additional year that goes by, the cost of a Super Bowl commercial is increasing by about $69,349.50. So let's go ahead and squeeze that in here. So for each year that passes, the cost of a Super Bowl commercial, here space is at a premium, so we'll say a Super Bowl ad like they did, increases by how much? By $69,349.50. Alright, so that's L. That's the one that we're used to doing. Now the new one would be for an exponential function. So for E, we're going to focus on the base, and the base is 1.064929, and that's what we're multiplying by every year. And remember, if you multiply by 1.0649, doing 1.0649 times is the same as doing 106.49% of, and this part above 1 tells you what percent increase you're getting, but it's telling it to you in decimal form. So when I see that, I would ignore the 1, move the decimal over a couple spots, and get 6.49. That's probably enough decimals, and that would be a percentage, and it's the percent that the output, which is cost, is increasing each year. So rather than saying that the commercials go up by a fixed amount each year, 69,000, I'm going to put it into a percentage term when I look at the exponential and say each year the cost of a Super Bowl ad increases by 6.49% compared to that previous year. So when you do linear, you're saying you get a constant rate of growth. Every year it goes up about $69,000. But with exponential, you're saying it's a constant percentage. But a constant percentage is not constant growth because it's of the previous year. So as the cost goes up each year, the 6.49 gets applied to that higher number, and we get a higher increase each year. So when things are growing exponentially at a percentage rate, you'll get this bend. When things are growing at a constant rate, like in a linear one, you'll get the straight line. So those are the two different interpretations that they wanted us to give. Alright, so now at this point, we're going to finish off with a couple more, and you're going to see that they finally are kind of on board with us that the better one to make predictions with is E, and so they're going to ask us to use E for both of these last ones. Alright, so let's read through part D. In Super Bowl, let's see, Roman numerals, that would be 36. In 2002, a 30-second ad cost $1.9 million, and that was the first decline in cost. Use E to help estimate the total loss in revenue from ad slots during Super Bowl 36, which was likely due to a poor economy that year. So they're telling us how much it really cost, but they're saying, look, we're probably going to get better estimates of what it should have been from the E function, so let's use that to make our estimate. 2002 is 42 years since 1960, so that would be E of 42. And we'd want to plug that into our exponential function. Let's just bring that in real quick. So that'd be 0.140625 times 1.064929 raised to the 42nd power. So let's see what the calculator says that would be. So 0.140625 times 1.064929 raised to the 42nd. And this is in millions of dollars. I get 1.974831. 1, 2, 3, 4, 5, 6. That would allow us to go to the nearest dollar. And that is in millions, right? So it's dollars, but millions of dollars. Okay, so the actual value of that ad was $1.9 million, and our estimate was this 1.97. So they wanted to see how much revenue was lost. So we would have expected $1.97 million. And they actually got, let's add another digit there, $1.974 million. I guess that would be a 5 because of the 8. And they actually got $1 million, or $1.9 million in revenue. And if we subtract those two, that tells us the difference between what we would have expected based on our equation and what actually happened. So you can see those 1.9s are going to cancel. So you'd be left with 0.075, and that would be millions of dollars. I think it's weird to talk about a decimal amount of millions. So if we move that decimal over 3 spots, or actually just multiply by $1 million, then we'd move it over 6 spots, those 3 and then 3 more, which would be zeros, then we would get $75,000. So it looks like they sold those ads for $75,000 less than they would have expected, and so every 30 seconds that poor economy, I guess, was costing them about $75,000. So I'm just showing you those steps again. If we do the 1.974831, we subtract the 1.9, that shows us the difference, and that was in millions, so times 1, 1, 2, 3, 1, 2, 3, so 6 zeros for a million, and then we get $74,831, or if I round it off, $75,000. Alright, and then finally, they want us to use E to predict the cost of a 30-second ad slot during Super Bowl, oh my goodness, my Roman numerals. I think this is 40 and then plus 8, so Super Bowl 48 in 2014, so how much should an ad have cost during that Super Bowl? So first of all, we'd figure out T. T is 2014 minus the starting time of 1960, so that's 54 years later. I think, what did I say that was? Super Bowl 48. Earlier they said the first Super Bowl was 1967, so there's some hope my Roman numerals were right there. And then how much would we expect the ad to cost in that year? That would be E of 54. So that'd be 0.140625 times the base of 1.064929 raised to that power of 54. And they're asking us to use E, and I would want to use E because it looks like the better fit to the data. So let's see what we get out of that. So 0.140625 times 1.064929 raised to the 54th power, and we get 4.201, and that would be millions of dollars. So if I multiply by a million, I get $4,201,243. So it kind of went back and forth on my decimals here. If you just left it like this, you could say that it's about 4,201,000. If I use the original number from the calculator, I can go to the dollars place. What you should do when you're working on the homework is see what the rounding directions are from my math lab and then follow those. So $4 million for a 30-second ad, and then think about how many of those ads you actually end up seeing during the Super Bowl. So they are bringing in a lot of money from those Super Bowl commercials. Alright, so here's the 4-step modeling process. If you want to find a model and make estimates and predictions, create a scattergram of the data and decide whether a line, a parabola, an exponential curve, or none of these comes close to the plot. So we didn't cover parabolas, so that would be one that we would leave out. We're looking to see, does it look linear or does it look like it's curving, and then we would go with exponential. And notice that even though they didn't ask us to do a scatter plot for this problem, they are suggesting in general you should do that. So even though they didn't ask, I did one because I want to have a look at which one looks like a better fit. Find the equation of your model. They had us find the equation of both the linear and the exponential for this one. I would argue that the reason you look at the graph is just so that you can pick which one would be better and just go with that. It is pretty easy to do on the calculator, so no harm in doing both and then graphing them both and seeing which one fits better, and then write that equation down. And then verify that your equation has a graph that comes close to the points in the scattergram. If it doesn't, check for calculations errors and so on. So I would argue that this step 3 is actually kind of happening before this, that we would want to graph those equations, both of them, the linear and the exponential, and then see which one fits better, and then write our equation down. And then use your equation to draw conclusions, make estimates and or predictions, interpretations of growth rates, like using the slope or the base, stuff like that. All right, that wraps up section 10.5.